Oh, what a day! What a lovely day!
Welcome to Flat Earth Debate Special Edition Live. I'm your host Nathan Oakley, and if you are new to this channel, or you've not done so already, then be sure to subscribe, hit the bell notification icon and join button if you'd like to become a Nathan Oakley 1980 channel member and keep up to date with the Flat Earth Debate. If you'd like to support the channel, there is a super chat that runs alongside each of these shows while they are live. There's also a PayPal, Patreon and crypto link in the info box below the video. Most importantly, if you'd like to join the discussion, you can't because this is a special edition presentation, so we're going to move over to Brian's Logic in a minute for his presentation on Geodesy. However, please be sure to share the show on Facebook and Twitter. So, we are also joined by Arwin, so I'll say a quick hello to our two guests. So, hello Arwin and hello Brian. Good to have you both.
Hello Nathan, hello Brian. Good afternoon.
Hey Nathan, hey everyone, hey Arwen, how are things?
Hello. So obviously no housekeeping as this is a special edition presentation, but you've given me a heads up and indeed sent me your presentation. So I've got a pretty good idea what you're going to be doing, and in the pre-show we discussed how it'll be presented, so we might respond to some of the people's chat comments, and hopefully if any of the other ballbusters or anybody that Brian sends the link out to wants to join, they can to ask questions or give comments. I'm happy to launch straight into the presentation if you're good with that, Brian, if you want to share your screen. So as I say, this has been gone over with a fine-tooth comb by Brian. Go on, Brian.
Yeah, I actually stayed up all night and only had a couple of hours sleep and was at it until about 7 o'clock this evening. So I'm hoping it's together well enough to be get the point across, because I have to redo what I did have. It's my fourth time redoing the presentation. I just tried to I had so much more information in there, but I had to take out as much as possible just to keep the thing as short as possible. If you just give me a minute, I just want to send a link to you, Chocolate, and then we can get going, if that's okay with you. You're coming through roboting a lot as well, Nathan. I don't know if that's... I said I better say it to you.
Is that me or Brian's end, Darwin?
I'm not getting any looping here.
Could be you.
So.
Could be you, Brian. I'll reset my desk anyway.
Could be me. Yeah. Could be me. If I... 1 second now. I'll come back in one more.
What? Where have you gone, Brian? Don't do this to me. I'm waiting on a presentation. don't worry about sharing the link now. Let's just get on with it. I'll share it with Chocolate. No worries.
Okay. Shall we get started then?
Yes.
I was trying to share it with Chocolate.
Yes, please. Yeah, don't worry about that. We're in the middle of a live show now, so let's just get on with it.
Okay, grand. Okay. Right, I'm going to share my screen and get started on it, okay?
Perfect.
Okay. Thank you.
As you're doing that, drum roll. Brian's Logic, smashing, Geodesy. Here we go.
Dum 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 dum.
Okay, anytime that you have any questions or anyone wants to ask, you have anything to say about anything, just come in and say it. Okay. Because that would definitely break up the monotony of it, because it is going to be a lot of stuff. People are out there in the chat. Some people will understand it and I've heard it before. A lot of people won't. You know, right, I reckon a lot of the board side won't know about it.
This is not monotonous. This is a good presentation. Have some faith in your own presentation. It is ace, and I assure the audience this is going to be riveting.
Okay, fair enough. It's just that the subject is just outside what people are used to. It's not going to be as easy a subject to follow. That's the point I'm making. Okay, okay. My presentation is called "The Truth About Geodetic Surveying and GPS." Okay. There is two branches of surveying: planar and geodetic. Planar surveying deals with areas of land under 100 square miles. They assume a flat earth. They assume all triangles are...
Are you breaking up, Brian? Do you want to just... Let's not start as we mean to go on. Do you want to drop from the Hangout and just try and rejoin? Unless it's your Bluetooth headset, God, I hope not. But drop and rejoin. We'll try once more.
Okay. 1 second now. Yeah.
In the meantime, some elevator music. Dun 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 dun. How are you, Arwen?
Yeah, that music doesn't really work when there's no baller in the waiting line waiting to be humiliated.
Oh, you need the tense, pregnant pause for that to work, do you, Owen? Okay, we're rocking. Let's just check Brian's sound, and then hopefully this will rock on.
Check 1, 2.
Yep.
Seems better. You want to present your screen again?
Yeah, will do. Sorry about that. Okay.
Another drum roll. Start from the top.
Yeah, I'll start from the top again. We can start it from the very top. Okay. This is a presentation I put together about the truth about geodetic surveying and GPS. Actually, a caveat I want to put in here is that I'm not accusing geodetic surveyors of hiding the truth or being in on a lie or anything like that. That is not the point of it. I'm just pointing out things to do with geodetic surveying that most people, including and especially people who do geodetic surveying, may not actually really be aware of. They just do what they've been taught to do, and they do it as a job, and that's what they do. Okay, so I'm not pointing the finger of conspiracy at anyone. Okay. Okay, there is two branches of surveying, planar and geodetic. Planar surveying deals with areas of land under 100 square miles. They assume a flat earth. They assume all triangles are on a flat plane. They do not expect to see or measure curvature to the earth. Geodetic surveying deals with areas of land over 100 square miles. They assume a globe earth. They assume all triangles are on a curved surface. They do expect to see and measure curvature to the earth. The word expect here is very important psychologically. And why I say that is if you're expecting to see something and you're told it's going to be there by the people who taught you that it's going to be there and they expected to see it, then if you don't immediately see it, you're going to do whatever you can to make sure that you do somehow see it or make it into reality. Planar surveyors don't expect to see curvature and or measure any curvature, and they don't. They never see it. They don't measure it. Geodetic surveyors do expect to see this and do expect to measure it. So they have to do. They have to work. They have to make things happen so they do somehow find this curvature or what they feel is evidence of curvature or of a globe earth, because that's what they're expecting to see, as that's what the people who taught them expected to see, and that's what they have to find basically in it, because they're expecting to see it. So that's why the word expect here is very important psychologically. That's why a lot of things in geodetic surveying would be looked past by people who work in it, as that's just kind of the way it is, that's just part of the job, and they wouldn't think about it simply because, including Jesse Kozłowski, they wouldn't think about it because that's just what they do all the time. Well, that's just the way it is kind of attitude. So that's a big part of why they can't show us and prove curvature to us. They can show it to what they believe will be good enough for themselves, but they can't show it to us. They can say we've got this measurement or that measurement, but then they can't actually show us. They can only give us figures and calculations. They can't show us the curve of the earth. Whereas planar surveyors never have that issue. They don't have it. They don't expect to see curvature. It's not there. They don't see it because it isn't there.
Carry on, Brian. If there's something to be interrupted with, we'll interrupt, I assure you. Brian. Brian. Brian.
Brian! We need you, Brian. Okay, Brian's having mic issues.
Yeah, it looks like Brian's having issues. We can't do this for 4 hours, Brian. Brian.
Hello, Nathan.
Hello, we've got you.
Yeah. Okay, 1 second now. I don't know what's going on here. This never happens, but I just
don't worry.
Join and do exactly the same as I do every day, and I don't know why that's happening.
Okay. if you crack on from where you were.
I will do. See. Can you hear me okay?
Yes. Do you want to crack on?
Yeah, okay.
Will do. Now, can you still hear me? I want to make sure this.
Yeah.
Yep.
Okay, I just wanted to make sure. That's all.
Sure.
Okay, so these are I'll start from here. These are the steps this presentation will take to explain how geodetic surveyors start off with a globe belief and convert it into our flat reality. Step 1, explanation of the globe earth assumption. Step 2, explanation of the role of the global ellipsoid and global geoid. Step 3, explanation of the conversion of these global datums into more localized datums. Step 4, explanation of the conversion from localized datums to XYZ flat Earth Cartesian coordinate systems. Step 5, explanation of GPS and its direct connection to geodetic surveying and geodetic surveying's direct connection to it. Step 6, finality of the presentation. Okay, so step 1, explanation of the globe Earth assumption. Okay, this is the globe Earth as we've been shown it. This is the famous blue marble photograph. I have 16 more miles right across this. Officially, the globe Earth supposedly has 16 more miles east to west as opposed to north-south. Why? Supposedly, according to internet sources, the oblate spheroid vision of the globe Earth was first postulated by Isaac Newton. Now, we don't personally know if this is true or false that he said this, but I will say that nobody of Isaac Newton's time could possibly have been able to say with certainty what the Earth is or is not. I am certain that if Isaac Newton could have taken a long-haul plane journey, that if he postulated the Earth to be a globe or oblate spheroid beforehand, that he definitely would have had second thoughts afterwards. Right? What I mean by that, why I'm saying that is, the internet says a lot of stuff, and it's true.
Sorry
Yeah,
for interrupting, but what's with this Isaac Newton?
Isaac Newton. Oh, I
Yeah,
might be having spelled wrong, do I?
2 S's. You like,
I meant to put in a Z, is it?
yeah, you misspelled it twice.
Oh, well, it doesn't matter. You know what I'm
Don't worry.
talking about.
Let's not criticize the typos. Who cares?
Yeah, you know what? It's just that's how we always spell his name. So I have a friend, and that's how he spells his name is Isaac, and that's how he spells his name. So I spelled it the same. Okay, so my point is that the internet is always saying this is real and that is real, but there's no guarantee that, let's just say, someone said something for definite or not. You see memes all the time where Bob Marley said this and Bruce Lee said that and so on. And it's obvious from reading it that most of these memes that they didn't say these things. And if you do a bit of research, you find out they didn't say those things. It's just things people make up. The same happens a lot with Isaac Newton, for instance, and other people. But Isaac Newton, it seems to happen a lot. A lot of things are attributed to Isaac Newton. Now, he may have said and postulated that the Earth is an oblate spheroid. I don't know, right? But I know the internet says that. So when the internet says it, people start believing it. If they look on the internet, the first thing they find is that Isaac Newton was the first person to say that the globe was an oblate spheroid, then people are just going to accept that and go with it. And so it's because of stuff like this that people, like, things are attributed to people because of who that person is. And then that gives the thing that's attributed to that person weight and validity. But he may not have said that. And my point being is that even if someone of his time, including him, did say something like that, right, they could not say for certain at that time what the Earth is or is not. And if any of them, including him especially, had taken a long haul plane journey, would they have had a different attitude afterwards? I would say definitely. That's my point about that. So that's the start. So the whole oblate spheroid thing is online. It's being attributed to Isaac Newton. Now, the reason I put that in is because I didn't know, and because the internet is saying that. It's like making an example of things that the internet says that may or may not be true. It might be true, but it might not be true, and people will just read it and accept it and go with it. So if he didn't say that, then why is it up on the internet? If he did say that, then how could he have known this? So it's kind of a 6 of one, half a dozen of the other. Okay, the godfather of modern geodetic surveying is Al-Biruni. Al-Biruni is famous for supposedly calculating the 3,959-mile radius of the globe Earth, but we now know that this is not true, as there is a wealth of observations taken daily of a moving and changing horizon line from all elevation heights. So it would have been impossible for Al-Biruni to have calculated any dip angle to any physical geometric horizon, as there is no determined definite position to the horizon from any elevation. There is only an average calculation based on an observer's viewing angle based on their observation height above sea and ground surface level. The horizon is a visual effect and not a physical location that can be relied upon to be there. The horizon is the apparent juncture between Earth and sky, whose position is determined by the weather, so it cannot be used with or in a physical measurement, as it does not have consistency of place. Right? My explanation for that, why I put that in, is that Al-Biruni is called online the godfather of modern geodetic surveying because he supposedly calculated this radius that we know is not true now. That there's no way he could have done it. Not just that he made a mistake or calculated something wrong or put out a dodgy calculation, right? He couldn't have done it because they can't. There's no particular place where you can see the supposed globe geometric horizon, physical horizon. You can't see this. This is what we're told all the time now. So my point here is that he couldn't have done this, but yet he's the backbone of modern geodetic surveying. So I'm kind of showing from the very start where they're taking something as a pre-assumption and calling it fact. And now he's the godfather of modern geodetic surveying. Someone who may or may not, I don't know if the man even existed, but if he did, there's no way he could have calculated anything to any physical horizon because the horizon is not a physical place. So that's my point about this. That's why I added in that part. Okay, step 2. Any questions about these? That's first step.
No, I'm keeping a fairly close eye on the chat. Oh, go on, Owen.
No, nothing to add here.
Okay.
Except the chat is going crazy.
Yeah, I'm sure I'm saying something.
It's Friday evening.
Sure, but there's nothing in response to what you're saying, Brian. So let's move on.
Okay. Step 2. Explanation of the role of the global ellipsoid and global geoid. Okay, on the left of the diagram is the representation of the global ellipsoid, and on the right of the diagram is the representation of the global geoid. The global ellipsoid is supposed to represent an idealized model of an average surface level covering the whole of the proposed oblate spheroid. So when the ellipsoid is referenced, what is being referenced is an average idealized surface level above mean sea level. That's based on an oblate spheroid. Whereas the global geoid is supposed to represent an idealized model of an average mean sea level, both above and underground surface level. So when the geoid is referenced, what is actually being referenced is an average idealized mean sea level above and under the ellipsoidal surface model. So up here, this is the WGS84 ellipsoid, basically. This is what it is. This is what we're referencing. And here with the wavy blue line over it is the geoid, which is supposed to be mean sea level. So these are starting positions, let's just say, for geodetic surveying. This is a starting position that they will reference the ellipsoid and the geoid all the time. Okay. Okay, definitions of an ellipsoid and a geoid. I said that this is important to put these in. An ellipsoid, a three-dimensional figure symmetrical about each of three perpendicular axes, whose plane sections normal to one axis are circles and all the other plane sections are ellipses. A geoid, a hypothetical solid figure whose surface corresponds to mean sea level and its imagined extension under or over land areas. So, right, both the ellipsoid and geoid are known as datums. Okay, before I get to the definition of a datum, so none of them are real. Like the ellipsoid, they don't say is hypothetical, but the geoid they do say is hypothetical. Yet the geoid is part of the globe model, right, let's just say. But we know that both of them are hypothetical, but they're just a starting point. Both the ellipsoid and geoid are known as datums. Here is the definition of a datum. Datum. A piece of information, an assumption or premise from which inferences may be drawn. A fixed starting point of a scale or operation. A datum is a piece of information, a starting point, an assumption or premise from which inferences may be drawn. So a datum is a fixed starting point, right? So an explanation on a datum is that these are datums. So this is the starting point for all geodetic surveying. They start with the globe, but the globe is not, let's just say, as I showed above, that's not considered a datum, not that I can find any evidence of. These are considered datums, the ellipsoid and geoid. So the supposed idealized surface of an oblate spheroid and the supposed mean sea level over and underground of that oblate spheroid. So that's their starting point. For all geodetic surveying, it starts there. It doesn't start on the ground, it starts there. And they work down towards the ground. That's what they do. So their starting point are literally diagrams. Okay. So some basics. Orthometric height. The height of a piece of topography, mountain, hill, valley, etc., above the geoid, which is mean sea level. Ellipsoidal height is the height of a piece of topography above the ellipsoidal idealized surface of the oblate spheroid model, and geoid height is the height of the ellipsoidal surface above an idealized mean sea level of the oblate spheroid model. So to give some kind of realistic view on this, the top orthometric height is just basically talking about the top of a mountain or hill or whatever, and its height above mean sea level. Okay, ellipsoidal height would be the basic surface level of what would be the oblate spheroid below the mountain or hill, let's just say, or in relation to the mountain or hill. And geoid height is just the basic, let's say, idealized surface level of an oblate spheroid between that height and between that and the geoid, which is mean sea level. But in a realistic terms, they're just talking about the height of a mountain above mean sea level, the height of that mountain, or let's just say I'm using mountain as a reference, mountain above the surface, the basic surface below, and then the height of the surface below above mean sea level. That's all they're referencing. But they add in the ellipsoid and the geoid because that's part of the belief of the globe. So they add in these things, even though the ellipsoidal surface and the geoid mean sea level often won't match at all with anything, even on a local level, but they still do. So okay, this is the WGS84 projection datum with dual radiuses. Okay, it has dual radiuses is wider at the east to west than it is north to south. Okay, this is the oblate spheroid. This is the flattening of the WGS84 datum, also known as the AE map. We all know this one. Okay, this is the flattening of that. Okay, when they do the calculation to flatten it out, this is what it is.
Well, one of.
This is all. Sorry, Nathan.
Well, it's North Pole centric azimuthal equidistant projection to give it its full name, but you can project that map from any location you like. They just happen to make it North Pole centric azimuthal equidistant projection of, as you put it, a flattened WGS84.
That's right, yeah, azimuthal, yeah. Yeah, they just flattened it from the center, that's all they did. Or from what they would, basically what they perceive as the North Pole. That's exactly it. And here is again, this is also the flattening of the WGS84 datum, the UN flag. Same thing again, just with the kind of an ad hoc latitude and longitude grid on it. Okay, this is the global geoid according to Google. Okay, this is supposed to be mean sea level according to Google. This is supposed to be a global geoid, right? So I wouldn't normally, I don't want to laugh in the middle of the presentation, but this is pretty ridiculous. Okay, but this is the geoid.
That's the space testicle. That's what Anthony Riley or Sleeping Warrior calls it, the space testicle.
Yeah, and this is basically what it's supposed to look like without water. This is but yet it's called the geoid, which is supposed to reference the mean sea level. If you Google geoid, you will get this, as one of the main images comes up for it. It's ridiculous. Okay. I don't have much to explain on that. That all explains itself. We all know all these things. I just have to put it in for the presentation. Sorry, for the sake of the presentation, I put it in.
But hold on, this is kind of a false dichotomy, the
Go on.
ball Earth, the supposed testicle Earth, and the disc Earth.
Yes.
Yeah, no, it's
The
just
UN
explaining
flag.
what it's just
So
explaining what they referenced so
what's
far.
the proof that the
It's not he's not
equator
presented a
is
dichotomy. Owen,
circle?
he's not presented a dichotomy. He's just explaining what they do in Geodesy so far. He's not presenting an argument. He's just doing a presentation.
I know. I'm just reading in between the lines.
Yeah, I haven't presented that yet. I'm just showing people what they start with, what the starting points are. So people can actually start understanding what they actually start with. They start with diagrams because that's all they have. They have no photographs of these things. They have only diagrams of them. Unless you want to believe NASA, NASA photographs, which no one is going to. But this is what you get. So if you are starting to be a geodetic surveyor, this is what you have to believe. This is what you have to start with. This is your starting point. It won't be what you end up with in your day-to-day life, but it's what your starting point is. That this is real. This is what you start with. So, before going to step 3, any questions on that, or are you okay with that?
Again, I've been keeping an eye on the chat and interrupting where I see fit, but so far, literally nothing from the chat has addressed anything you have said. Literally nothing. So I'm happy to move on.
Okay, that's great. That's fine. Okay, 1 second now. Quick sip of water. Okay, step 3, explanation of the conversion of these global datums into more localized datums. This is important, this part. It's at this stage in the process that these global datums start to be localized. The reason for this is to focus on a particular area, be it continent, country, or state. Okay, so if you can see here, this is the main ellipsoid here in green. You have the geoid in the wavy blue around it. The red area is when they start localizing an area of it. So let's just say the red area could be Europe, right, or the US or whatever, okay, and they start localizing that, okay. So once they start localizing it, then they end up with diagrams like this, and diagrams like this, which start to look more like reality. Here we can see where the curvature of the previous datums has receded greatly. Once things are localized enough to bring things to a realistic level, the closer to reality we get, the less curved things become. This section is very self-explanatory. They localize a section of the global ellipsoid and global geoid datums and proceed to remove the curvature we don't see until they have localized these datums to a point where they start to represent the reality that we see and know. This is a very important point in the process of bringing the globe model and our flat reality together. Okay, so this is what it is. When they start localizing everything, they can start saying, "Oh well, we don't really see as much curvature anymore." You know what I mean? They can start kind of hand waving away the curvature that they don't see, that they think that this is the curvature they don't see. They can start hand waving it away, but they still only have diagrams at this point.
It's not hand waving; it's downplaying it.
Yeah, it's well, I mean, if they really went looking for it, they wouldn't find it. So they have to hand wave it or downplay it, whichever. It's the same thing. They have to.
But the
Because all they've got is diagrams.
The downplaying is basically, making it so small that it eludes the senses. That's basically their final strategy.
Well, yeah. If you look at these, go on, Nathan.
I was going to say you had one on-topic comment from Sleeping Warrior. He says he's under the impression that the space testicle, as he calls it, is actually a representation with the colour mapping of the presupposed gravitational effects on the chubby ellipsoid. So it might be something other than you're under the impression of, because I think he was correcting you saying that it's the Earth without water. I don't think that is the case. I think, well, I'm under the same impression as Sleeping Warrior.
Yeah, I would have originally seen that too myself. Originally, I would have seen exactly what you're talking about. But when I went looking online, this is what they're calling a geoid. And I went looking online, they're calling it a geoid, and I've seen it even on a website. Like they're literally calling this a geoid.
Okay.
And, I knew when I was putting it in there. I knew when I put this is actually. I'm very happy with this. I knew when I was putting that in there that there could be someone say, "Hey, what about this?" Or that's not exactly that, but it doesn't matter because it's all fantasy anyway. It's not real.
I see. So what you're
So
saying
it
is
can be
no,
anything
that
you
is what they claim. The geoid is what they claim. Now the color mapping on it might be the gravitational bullshit, but the shape and size and whatever scale is what they claim we're on. That's the geoid, right? So therefore, sorry, Sleeping Warrior, it seems like no, he's standing by what he's saying. Maybe you're just right with the color charts that are on it.
No, I mean, my point is that he might have a very good point, because I did hear that when I first saw that diagram myself a couple of years ago now. When I first saw it, it wasn't nothing to do with a geoid. No, I wasn't looking at it for that reason. But the explanation that I saw online for that wasn't to do with mean sea level. But it's been called a geoid online. And like, this is the kind of point I'm making with the first part as well about Isaac Newton. Like, stuff has been called stuff online, and it may or may not be correct. Now,
Okay.
it doesn't really matter whether that's the geoid or not the geoid, because the geoid is fantastical anyway. It doesn't
Right.
exist.
Okay. It's. I see what you're saying. It's all nonsense anyway. But like I say, Sleeping Warrior's apprehension is that particular brand of nonsense is the fluctuations in gravitational distribution or something to that effect. So just let's move on.
Yeah, I can't argue with him. You know what I mean? Because one diagram is as false as the other. You know what I mean? So I can't argue with that. You know, but I mean, as I said when I first saw it, it didn't say anything about mean sea level, but now online it's down as an image of a geoid. You know, so but I wanted to show that because it looks so ridiculous. Because it's as ridiculous as if I showed a more basic geoid, we just show exactly what I showed earlier, which is a wavy blue line in a going around an ellipsoid kind of a shape. So you know, one is as false as the other. You know, because none of them are real. You know, but he has a point. I can't say that I'm correct to put it in there, because he could be right in what he's saying. But it didn't matter. I knew that could happen, but it didn't matter because it's all false anyway. That's my point with the whole thing. Because
If I may insert for a second, to quote Chaiki, on a flat Earth we don't have a horizon.
Well, he's wrong there.
Yeah, for sure.
Yeah.
Okay, right. I think we've covered the geoid. Let's feel free to carry on.
Move on. Yeah. Okay. 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 So the last thing I said was this is a very important point in the process of bringing the globe model and our flat reality together. Okay. So it's self-explanatory. Basically, these are basically showing how the curvature of the previous models seem to disappear once they start localizing it, and that's what and this is important. That's what they expect to see, right? This is what you get here a lot. That's what they expect to see. It's what they're expecting, you know. So that kind of helps them as well. Mentally, helps them psychologically, because then they can keep saying this is what they should see. They shouldn't be seeing curvature. You know, this is what they can tell themselves. Okay, the reason this point is so important is because up to this point, from step 1 to step 3, there has actually been no surveying done whatsoever. Everything is pre-assumed. And it's not until we get to this point in the process that we are close to actually surveying anything. And it is this point that the geodetic surveyors play a trick on themselves. They survey such huge areas, more than 100 square miles at a time, that they must reach a point where the line between reality and belief is very thin. And it's at this line that they suspend their flat reality in place of a globe belief. Right? My explanation for this is that because they're working in such big areas, that they can assume that it's a globe and get away with it. I will show later on what helps that, but they can assume that it's just a really big globe and get away with it psychologically for themselves, because it's like the area is so big they can't actually see. I mean, if you had let's say a P1000 camera with an IR filter, would you be able to see 100 square miles in a 360-degree view? No. Now, what they do is they use triangulation. So they start off with an actual measurement, and they triangulate from that measurement to give them a distance and to somewhere and whatever else to map out to survey a place, an area. But they then can put that together with other ones and use parts that they're going to go into later to do with GPS that allows them to believe that they're on a globe, but they never see this curve. They don't find this. They never see it. If it was there, these are the people who could show it to us. And in 5 years, they have not been able. So the point, the line I'm talking about here between reality and globe belief, flat reality in place of a globe belief, is that it's like this point where, well, I don't see any curve, but we know it's there. It's this kind of thing. And we've heard this a lot. It's like you can't really see it, but it's there. And it's more the globe stuff like that. And they're able to tell that to themselves, which allows them to do their daily job. Because that's what they're told. Well, it's there. It's just like these are all the calculations for it, and they have every calculation and measurement, but they don't have any actual, any physical showing proof to show this supposed curve. They don't have it, and things that they supposedly do have, or what I'll show later on in the GPS section, is nonsense when you see what they actually do and the trick they actually play upon themselves. But this is the start of it. When they are at that point where they're trying to survey such a huge area, they can call it a globe if they want, because it's all in sections that they're surveying this, and they can't see the whole lot in one go. As I said, even with a P1000 camera with an IR filter, you won't be able to see 100 square miles in a 360-degree view. And even if you could, there's lens distortion and other things that could help you believe it's a globe if you want it. So I mean, this is the point I'm talking about here. That's why I'm giving an explanation of that, of why I'm saying what I'm saying here. Okay, so we'll move on. Okay, this is a little bit of literature on the subject. Okay, the orthographic map projection portrays the Earth as it would be seen from space. Meridians of longitude are shown converging towards the North Pole, with parallels of latitude running perpendicular to the meridians. Okay, a map is a planar depiction of a round reality, and it's a mathematical fact that such a depiction cannot be free of distortion. Planes are fundamentally different than spheres. It is important to concoct some magical mathematical formula to convert one to the other without distorting their geometrical relationships in a significant way. It might be said, this is an important part, it might be said that the role of geometric geodesy is to bring the world of the round and the world of the flat together. And that's exactly what I'm talking about up here. They have to make a globe out of the flat plane that they don't see any curvature on. And this is what they do. And as I said, it'll become more obvious later, but this is what they do. And so they have to make something out of something that is not. They're trying to fit a square peg into a round hole, and they do it somehow every time. Well, it's like a belief thing with them. As I said, I'm not pointing the finger at any of them in particular. They're just people doing their jobs, and they go along with the pre-assumption that they always had, that this is real. Okay, so that part is very important, because they are bringing the world of the flat and the world of the round together in what they do. Now, disclaimer, this is important. This is important, I have to put this in. Neither the globe, oblate spheroid, ellipsoid, or geoid are actually real, as besides many other factors, there is no physical geometric horizon available for scrutiny, so hence no globe Earth or any divination therein of it can be taken as fact or treated as a reality. That's an important disclaimer, because we've been doing nothing but looking at diagrams up to now, and people do end up believing these diagrams. But these things aren't real. They're just diagrams. They can't show them to us. If they could show them to us, in 5 years, they would have been able to do it. They can't. It's not there. And they don't have an horizon, right? They don't have a physical geometric horizon, so they don't have a radius. That's it. But if you start off learning geodetic surveying and all these pre-assumptions of all these models and all these diagrams are what is reality, is just too big for you to see, blah blah blah, then you're going to go along with the whole thing, and this is what you do, and that's your job, and it's a difficult job, and it takes intelligence.
Just lost your audio, Brian. Brian, can you hear us? Because we can't hear you.
Friday night.
Maybe time for some more elevator music. Da, 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 da.
Can you hear me?
Yes, we can.
Hello?
Right, let's move on, Brian.
Coming
Nathan?
through loud and clear. Can you
Yeah,
hear us?
Yeah, he can hear us. We can hear him. Let's carry on. Excellent. Let's not lose the flow. Oh, no, he couldn't hear us. Clearly. Wonderful.
Hello?
Hello. Right, do you want to share your screen? Hopefully we can carry on as quickly as possible without losing the pace.
Hello?
Hello.
Nathan, well, I don't know what's going on and why this keeps happening.
Don't worry. Don't explain it. Just get your screen shared and we'll carry on so we don't, we don't want to lose the audience's attention.
No worries.
Look, we can hear you. Just carry on.
Okay. So, did you see this part about the disclaimer?
Yeah, we've had all that. We just
carry on.
don't.
Okay, that's fine.
Let's move on.
We'll move
Hey,
on.
Adam, by the way.
Okay. Any questions on what I just said? This is the end of that step.
No,
Step 3.
we're all good. We're all good.
Okay. Fair enough. Okay. Explanation of the conversion from localized data. Step 4, sorry. Explanation of the conversion from localized atoms to XYZ flat Earth Cartesian coordinate systems. There is 2 main versions of Cartesian coordinate systems. One is 2-dimensional using XY coordinates, like on a physical paper map, and the other is 3-dimensional using XY and Z coordinates, like on a digital device where there is a 3D maps available. Other coordinate systems that intermingle with Cartesian coordinates are ECEF coordinates and geographic coordinates. Geographic coordinates are just the latitude and longitude grid, so they pre-assume a globe immediately. ECEF coordinates are a mutation of Cartesian coordinates and geographic coordinates. ECEF coordinates use the XYZ Cartesian coordinates, but the Z-axis is always pre-assumed to come from the center of the globe Earth via the North Pole, with the X and Y axes are projected out at the equator line with the X-axis at the prime meridian. Okay, so the ECEF coordinate system is what gives us the WGS84 and other projections, and is used by geodetic surveyors for this reason. It is also the supposedly most used coordinate system by satellites. No surprises there. Okay, the ECEF coordinate system allows for 2 things. One, it allows for the use of Cartesian flat Earth coordinates while still maintaining a globe belief. 2, by doing this, it makes the change from Cartesian XYZ to geographic latitude and longitude easier. As all Cartesian XYZ coordinates eventually become geographic coordinates, as latitude and longitude is what the globe belief uses. ECEF stands for Earth-centered, Earth-fixed. Okay, sorry.
I did not know that. Did you know that, Adam or Arwin?
Well, very detailed information.
I didn't know that. That was ace. Moving
Okay,
on. Adam, have you got anything to add? If not, we'll move on.
Okay, we'll move on then.
Move on.
Okay, this is the basics of the ECEF coordinate system. This is just, it's not how they actually use it, but it's how they pre-assume it. The Z here, the Z-axis, the zenith, is always through the North Pole. The X is out at the prime meridian, and the Y is out the opposite way, out at the equator. It's what they call a right-handed, I can't remember the name for it now, but it's a right-handed, you use your right hand to show it, basically.
Let's get it pegged. Adam, are you there? What's that symbol between that? Looks like a right angle between X and Y. Can you see that little symbol? I don't know that symbol. Do you?
Which one do you want me to do? This one?
No.
Or this one?
That one. Yeah. That's what you were referring to, was it not? Was that not what you were referring to? Can't hear Adam. Can anybody else hear Adam?
I can't hear Adam at all, no.
No sound of Adam.
No, nothing from Adam.
No,
You might have to come back to it. Carry on with your point, Brian. Sorry.
Yeah, no worries. No, this is just a basic layout of the ECEF coordinates. This is not actually how to use it. but this is the starting. It is how to use it, but it's not how to use it. As you'll see soon, this is the starting point of self-deception, basically. Okay.
We got it from Travis. It's Lambda. Thank you very much. The Plain Truth. Subscribe today. He's got a channel.
Yeah.
Thanks, Travis. Okay, the tangent plane. This is part of what we've just been looking at. To use XYZ coordinates, you must use conjoining right angles to make a rectangular box. So all XYZ coordinates make a rectangular box. Okay, and that means you have to use conjoining right angles. For those out there who don't understand, this is a right angle. Okay, that's a right angle. Right, which means it has to be on a flat plane. It always has to be on a flat plane. For them to join, it has to be on flat plane because they don't go over curves. Right angles, they don't deal with curves, they deal with corners. Okay, this is a tangent plane. Okay, now look at this here, this dotted line coming into this green, let's say it's called a green flat plane here. Okay, this is going to start adding up in a moment. Okay, this is important. This line coming in here to this flattened place here. So the rest of it here is of this diagram shows a curve, but this one particular area is a flat area, one flat plane. Okay, here we have a curved surface with a flat grid on it here. Okay, another flat plane on a curved surface. The tangent plane creates a flat plane out of a section of the ellipsoid surface. So there can then be a perpendicular line from zenith at that position. Meet the now horizontal flat plane to create a right angle at that point to create Cartesian coordinate systems so surveying can take place. So this here, this tangent plane and this line coming in here, which I'll explain soon, right? This line is a zenith and it allows, right, and because it's a zenith, right, it has to have a perpendicular to, it has to be perpendicular to a plane. So they have a plane and they have a zenith. So then they have a right angle to work with. Okay, and this is when actual surveying takes place. Okay, at that point.
Hold on, let's go back to make it bigger. Sorry. So where you've got line H, perfect. This is your assumed point. You are standing as H, and your zenith is that line. So your zenith obviously comes out the top of your head, and you are standing on what they describe as a tangent plane, so that you can have your 90 degrees. Correct?
That's correct. Yes.
Okay. This is what Bev talks about all the time. Cool.
Yes, this is exactly what Bev talks about, and this is what Bev will be taking apart with the mathematics.
It feels to me a lot like basically a presupposed globe Earth that's being, grafted into the imagination of what's going on.
Kind of grafted under. So it's a presupposed sphere Earth under a tangential plane. That's what we're getting described so far, Arwin. This is fascinating. Do you want to move on, Brian?
Yes. That's exactly what it is. They have to add in a plane to do surveying because they have to survey a plane. That's what they do, regardless of what they say. This just shows it again here. Okay. They have right. So
hold on. Can you zoom out one more notch?
Sorry.
Make it smaller slightly.
Yep. How was that?
Perfect. Yep.
Okay. They have to make it flat before they can survey it. This is the truth of it. Okay. Now, this diagram is a fantastic example. Now, this will explain a lot. Okay, this here, this green square, this is your tangent plane that they just showed up there. This here, it starts off down here at the center of a pre-assumed sphere. This is your zenith. Okay, so up from the green square is your positive zenith, and down is your negative zenith. Let's just call it, right? But your zenith is not, it's at a 90 degrees from where you're standing on the supposed sphere Earth, right? The supposed globe Earth, okay? But it's making a tangent, to the center of this supposed sphere. And then you have the north and the east here, which is the X and Y. So this is the X and Y, okay, here. So you have X, Y, and Z. This is this here. Once they have the tangent plane and the zenith that goes to the center of a sphere Earth, they then start taking this whole area and making it into Cartesian coordinate systems. That's what they do. But this is the trick. I don't know if I'll say it exactly right. In the above diagram, it shows that it's not until this point that any actual surveying takes place. Okay?
So this is, of course, the process of presupposition, and it's utilizing the same method of the, I can't remember what you said, Earth-centered, EC, what was it? What were the initials? With the
EC, Earth-centered, Earth-fixed.
Earth-centered, Earth-fixed method. So you've got what I described earlier, or summarise what Brian said, with the word up. That's coincidentally for us in the UK around where they place the UK, give or take. So your up is you standing at that position, and all of these presuppositions and assumptions are being made prior to any actual surveying taking place on the tangential plane. I think we're all square, Brian.
Yeah, that's exactly it, Nathan. Exactly. Okay. Okay, this is a 3D Cartesian coordinate system. Okay, here. Okay. So this here, the flat part of it here, that's your tangent plane. Okay, this Z here, this is your zenith. What they show up here as this up. Okay, this is your zenith. And then you have the X and Y. This will be east and Y will be north. Okay. This here, right, is supposedly going down to, if you follow the line, sorry, my hands are a bit sweaty, it's hot here. If you follow the line, it supposedly goes down, in their belief, to the center of a sphere. Okay, but this, if you look here, this is a rectangular box, and they just make the whole thing a huge collection of rectangular boxes. That's what they do. And then they move on to the next tangent plane. But there's a thing, I won't say it now, I want to say it, but I won't say it now. I'll say it'll come in later on. There's a trick they play on themselves that allow them to believe that it's a globe, and you might spot it before I even say it. But they play a trick on themselves, because this is what they end up surveying using these Cartesian coordinate systems. This is what they end up doing. But they, as you know yourself, as you just said a minute ago, and as everyone else there knows now, that they have to pre-assume all this stuff before they ever do any surveying. So this is the first point of actual surveying, what they're doing here now. Okay, I'll move on. Okay, what is a Cartesian coordinates with example? Okay, the Cartesian coordinate system uses a horizontal axis that is called the x-axis and a vertical axis called the y-axis. Equations for lines in this system will have both the x and y variable. For example, the equation 2y plus y equals 2 is an example of a line in this system. It's just a way of reading it. Okay, here's another Cartesian coordinate system definition. A system in which the location of a point is given by coordinates that represent its distances from perpendicular lines that intersect at a point called the origin. That would be the zero that your starting point is. A Cartesian coordinate system in a plane has two perpendicular lines, the x-axis and the y-axis. In three-dimensional space, it has three, the x-axis, the y-axis, and the z-axis. Compare polar coordinate systems. But there's another one called a polar coordinate. There's several other coordinate systems, but they're not 100% important right now. Okay, definition of perpendicular: at a right angle of 90 degrees to a given line, plane, or surface, or to the ground. Right, definition of perpendicular too: standing at right angles to the plane of the horizon, exactly upright, being at right angles to a given line or plane. Okay. Plane, a flat surface on which a straight line joining any 2 points on it would wholly lie. Okay, adjective, completely level or flat. Plane in geometry, in mathematics, a plane is a flat two-dimensional surface that extends. Horizontal, right, definition, parallel to the plane of the horizon at right angles to the vertical. This is a right angle. Again, this is the definition of, this is a right angle. This is the definition of a rectangle and a box. A plane figure with four straight sides and four right angles, especially one with unequal adjacent sides in contrast to a square. Box, a container with a flat base and sides, typically square or rectangular and having a lid. Cartesian coordinates are all based around a three-dimensional rectangular box. That's what they are. no matter who uses them or what way they pre-assume whatever they want beforehand or afterwards. When you're doing anything with a Cartesian coordinate system, you always use a rectangle. You always make everything into a flat, a motionless plane. If it's a 2D, if it's a 3D, it's a rectangular box. For example, I think it's called X Plane or something like that is the name of it. It's software that's only out since last year, I think, and it's very highly accredited. That's for it's pilot training software, and the person who made it made all of it with Cartesian coordinate systems. So all pilots are learning through this software. Let's just say when they're learning how to fly, right? All these commercial pilots, when they're learning how to fly, all these young pilots now, they're all learning with this particular software, right? This X flight or X plane or something, and they're all learning to do this with Cartesian coordinates. Okay, so all these people who are going to be flying these massive jets around the world are all learning how to fly over a flat and motionless plane, because that's what Cartesian coordinates, whether they be 2-dimensional or 3-dimensional, they always reference a flat and motionless plane. So that's what these people who are pilots now, right, and they always perform in older software. That's what they're learning all the time. And Wolfie 6020 actually made a video about this software and was saying how it proved the globe. He actually didn't know what Cartesian coordinates were. And who let me know about it was Gleam. Shout out to Gleam. He let me know about it. And I went to Wolfie's and I posted up the video, the guy who made the software. I posted this video to Wolfie's video to show that he didn't know what he was talking about. You know, so like even he didn't realize that this software was referencing a flat and motionless plane. All Cartesian coordinates are, and they always do. Okay, moving on. Any questions before I move on?
I'm good.
Okay.
I like
can you hear me, guys?
We can hear you, Adam.
Yeah, we can hear you.
Did you have any questions?
Sorry,
You're a bit
it was
hot.
Lambda, Nathan. I was shouting.
Lambda, yeah, we got it from
Sorry,
Travis. Thank you.
I've got a quick question, Brian.
Okay.
Yeah, as you described that, I mean, for me, then, do they then have to back calculate a little bit like they do when, in terms of celestial angles, where they back calculate it based on a presupposition that the celestial angle is, from the center of a presupposed ball? Are they then, when you're taking measurements, now obviously for surveying, you take the measurement, you use it because it is a flat plane. So for all practical purposes, you use that. But if you were then to have to pre-transpose those coordinates back into their ball, you're going to have to subtract on the Z.
Yeah, I want to show in a while. That's a great question you're asking. What you're asking is it like I'm not surprised you're asking that. You're going to see in a while what it is. It's so simple and so stupid, but this is when you see what actually happens, you can understand why they can go, all right, that's okay then. And it all comes from the pre-assumption in the first place.
Well, what you've showed so far, I think, is part of it. Part of it is to engage the academic brain into a fantasy that they're engaging in science, and that what they're doing is they presuppose this a geodesic WGS80 format, and then they do it this, and this, and they're given these numbers where they think they're doing something, but all they're doing is measuring on a flat plane. It's all about engagement, buying into it. For me, it's selling the story to you.
Right.
It's a bit like the gravity bullshit and Newtons and the way they got ships to weigh something, then convert it into Newtons, transport it across, unload it, weigh it, convert it back into Newtons, and check the Newton weights. Where all you've done is times by 10. Frankly, at both ends, it's engagement to think you're doing something. But in reality, it's just shuffling numbers around reality.
Yeah, Brian did a very good job of going through it and highlighting it nice and concisely at the stages where they've not actually done anything yet. But it seems like we've done a lot with a lot of nonsense, but we haven't actually done anything. So yeah, it's just giving them something to keep them occupied to make it seem like they've got a purpose. and then you do some surveying once you've got your assumed nonsense and your tangent plane to work with. Then you can go forth and actually do something. But by then you've already, engaged in effort, and obviously it's all very precise, right? Well, no, it was all nonsense and unnecessary.
That's what that map, that kind of 3D map with the square coming out, hitting on the square map on a tangent plane. That kind of is the bullshit. You're convinced you've got to set this up nice and accurate first. That tangent's got to be right on that ball. It's got to be. No, you just got to drop a plumb line. It's flat, mate. No,
yeah.
Yeah, that one, Brian. Yeah.
Yeah, that one. Yeah, they have to complicate it to make it sound intelligent. With everything, people now believe that if something is not very complicated, that it's not science or it's not intelligent. When the simple reality they can't understand, and that's the biggest problem I think Flat Earth has. It's such a simple reality that people can't take on board how it can be more correct than all this complex nonsense.
That's the thing, though, Brian, isn't it? That the way in which you set up this complex nonsense is to drop a plumb line on a flat plane, on a flat Earth. That's the reality of how they ascertain that Z coordinate. There's none of this real nonsense where you're aligning it across a tangent on a ball. You drop a plumb line on a flat plane. That's how, in reality, we ascertain that, no matter what maths.
Very well. Hold on, I want to elaborate on what Adam's just said. We're saying the same thing over and over again, and repetition's good. So, for the audience's benefit, where I'm drawing this line here with up to this tangent plane that Brian so concisely described, well, when Adam says you're just dropping a plumb line, if we assume that this is Ireland and this is Scotland and this is England down here, well, this is roughly where they place us on a ball. And when you assume all of this nonsense to get you to this stage, what you're actually going to do to start the process is drop a plumb line. Now, that plumb line, from your vantage point, is just going to go straight down, and you're going to be capable of drawing a 90-degree to it. But all it does is establish this Z. Up is your zenith, and it's going to be assumed to be coming out of a ball at this angle if you're in the UK. Well put, Adam.
Yes, exactly. You have it so spot on. I nearly don't even need to tell you the rest. But
yeah, but let's get to the GPS bit anyway.
Good.
Okay, right. I'll move on to. Right. Okay, so I finished here. Right, Cartesian coordinates are all based around a three-dimensional rectangular box. Okay. Now, GPS data correcting using encoders and inertial navigation system INS sensors, right? Heap of nonsense, right? The GPS is something they make out to be this super brilliant thing as well. Look, local geodetic or tangent plane. The local geodetic frame or tangent plane frame is the northeast down or northeast up, okay? Rectangular coordinate system we often consider on our everyday life. So they're telling you here, right? They're telling you here that they're using Cartesian coordinates, this one place here, the same diagram as above. It's just done slightly different, but it's done the same, but made in a different program or something. But same exact thing. You have your Z, right, which are pointing to here, right, and your Y and your X, right. They have that a bit wrong actually. It should be the Y up to it, but it doesn't matter. But but the point is that they are telling you that they're going to be using rectangular coordinate systems here, right here. This is basically what they're telling you. Okay, and it is determined by making a fictional tangent plane at the origin, right? Which is origin is 0. Just want to show you, origin will be this point here, at the exact point where the X, Y, and Z would be originating from. Okay, it is determined by making a fictional tangent plane at the origin, just like representing the globe as a map. The x-axis points north, the y-axis points east, and the z-axis points towards the interior of the Earth, normal to the reference ellipsoid. So, this is more the same. They're telling you they're going to be using rectangular coordinate system, but they're going to also send the zenith into the center of the Earth, right, of their believed globe Earth. Okay, how to read Cartesian coordinates. I'm not going to spend too much time on this. Just give people a rundown on it. Anyone can learn this. Cartesian coordinates can be used for locating points in 3 dimensions in this example. Okay, 0 is here. Okay, so I'll try and show you as much as possible. The 0 in the center is your starting point. It's called the origin, right? From here, you start with the x-axis, which is this one, right? If you read the x to the right, it's positive. If you read it to the left, it's negative. So this is a positive reading of x. This is a negative reading of x. Then you read the y-axis. If you read the y forward, it's positive, and if you read the y backward, it's negative. So, sorry, now this is forward where the y is. So forward is positive, and backward is negative.
I'm glad you said that, Brian, because that means the numbers are wrong. It should be -245.
As opposed to saying negative.
Yeah, shouldn't that x coordinate be a negative?
Yeah,
I'm not just being a geek. I'm sorry, but
no, you're right. No, it is plus to the right and minus to the left. But I just use the words positive and negative.
The other z and y coordinates are positive, even though they're placed in a negative position.
Is the issue that where you've got 2, 4, and 5 in brackets, Brian hasn't put a minus next to them?
Just on the 2.
Well, I didn't write that. That's someone else's.
I know. I wasn't picking Brian up. Yeah, I knew that. That's why I said it, Brian.
It's just 2. Sorry. So I just want to be clear, just so the error is corrected. So on the x-axis, going towards the left, it would be -2. Is that the only correction?
Yeah. The coordinates should read -2, 4, and 5. If you look at there's a positive increase in the z-axis, and the y-axis looks is going up, but it's the x that's going to the left, which is
it's good. I'm glad you've corrected it. Good.
Yeah. This is someone else's diagram. I just got it online. The reason there was other ones I could have got, but this one has some color to it. So for the reasons of the people being able to see it on their phone on YouTube, I thought it's better to have the colored one, even though I know it's not correct. Here is not correct.
Sure, but a misspelling of Isaac is irrelevant, whereas this, you detailing how the system works, and if there's an error in it, that's pretty crucial. It needs correcting. So yeah, good job, Adam.
Yeah. I don't disagree. And then the x, then you read the z-axis last. If you read the z downward, it's upward. Sorry, it's positive, and if you read the z downward, it's negative. So I was ignoring this box completely. My point being is just this would be minus on the x. That would be plus on the x. This would be plus on the y and minus on the y. This would be plus on the z and minus on the z. So that's all it is. It's just three-dimensional. Maps, you'll often see maps with just the x and y on them, just without the z, because they don't have 3 dimensions. All the lines are numbered, starting at 0 and going right, left, forward, back, up and down. So I just threw that in just so people could have some idea of how Cartesian coordinates work, rather than just saying Cartesian coordinates for the whole presentation and not showing anything about them.
No, all good. Okay. No, worthy explanation. Cool.
Okay. Okay, the state plane coordinate system is a system used in the United States where all of the states are treated as Cartesian coordinate systems, which is exactly the same as the rest of the world, as everywhere is treated as Cartesian coordinate systems. They can't survey without doing that. Here is some literature on the subject. Okay, so the state plane coordinate system was established to provide a means for transferring the geodetic positions of monumented points to plane coordinates that would permit the use of these monuments in plane surveying over relatively large areas without introducing significant error. A plane rectangular coordinate system is by definition a flat surface. Geodetic positions on the curved surface of the Earth must be projected to their corresponding plane coordinate positions. Projecting the curved surface onto a plane requires some form of deformation. Imagine the stretching and tearing necessary to flatten a piece of orange peel. Now, the rest of it won't matter. I won't go into the rest. It's not important to it. To map the world more accurately, GIS uses a variety of geographic coordinate systems and projections. A GIS is a geographic information system. That's what the GIS stands for, Geographic Information System. The basic idea behind geographic coordinates is to convert a 3D sphere or spheroid into a flat map. Okay, when they're talking about geographic coordinates, they're actually talking about latitude and longitude. Okay, the article goes on at length about the WGS84. This is not important. Right, go on to this part here. The projected coordinate system begins with an idealized model of the Earth, a geographic coordinate system. The latitude and longitude is an idealized model of the Earth, and then uses a projection to convert a portion of the curved surface of the Earth into a plane. The round Earth coordinate system is described as an idealized model of the Earth. What we just talked about a minute ago concerning the zenith into the center of the supposed sphere. The idealized model of the Earth they're talking about here is the latitude and longitude grid around the sphere. And when they're talking here about using a projection to convert a portion of the curved surface of the Earth into a plane, the round Earth coordinate system is described as an idealized model of the Earth. What they're talking about there is they're taking a part of this just as basically the tangent plane we've just been talking about. That's what they're referencing here, the tangent plane, without actually saying it. Basically, they're turning a part of the supposed curved sphere out into a flat plane with Cartesian coordinates. That's basically what they're doing. And they start off with a zenith to the center of this presupposed sphere.
What's the phrase, Brian? What's the phrase? Hidden in plain sight. So it's the words that come to mind there, mate. Just to read it, The projected coordinate system begins with an idealized model of the Earth, and then uses a projection to convert a portion of the supposed, I insert in brackets there, curved surface of the Earth into a plane, right?
Yeah.
What they're saying is that we pretend it's a ball, then we treat it as it's flat, because we have to treat it as flat, because as it says in the next bit, curved section of that model temporarily reprojected, so we have to pretend it's flat, into a planar maps to gather accurate distance and measurement data as we so the only way to do it accurately is to treat it as flat. Well, surely if you were going to do it accurately, you would have to treat it as it is.
Exactly. That's exactly it. The exact point. Yeah. Because according to this literature, the whole idea of the latitude and longitude geographic coordinate system is purely to help turn the sphere world into a flat world. And this basically helps them. What I'll show a bit later on in the GPS section, what you see there, what I'm going to show in the GPS section will be very obvious. And it'll show how easy they can go from Cartesian coordinate systems to a latitude and longitude grid around the sphere. And this is like literally the latitude and longitude grid helps them turn it into a flat world. And as I wrote here, an idealized model of the Earth also means what you want the Earth to be. And what you just said, Adam, is spot on, because basically what they're doing, they're telling you in plain sight, hidden in plain sight, that what they their idealized model, what they want it to be, but for accuracy, they have to do the opposite of that. So what they believe in and what is the reality are two different things, is what they're telling you. They're telling themselves this without realizing it, I think. Just one part here I missed out. Spherical coordinates are projected to the plane coordinates, not the other way around. Further, they must be projected, which supports exactly what you were saying, Adam.
Yeah. It's lovely, isn't it?
Yeah.
Cool. Should we move on?
Yeah. Okay, don't need for any explanation there. I said whatever I needed to say there. Okay. Step 5, explanation of GPS and its direct connection to geodetic surveying and geodetic surveying's direct connection to it. Before I get started on this, I have to say, I had to redo the whole presentation and chop it down and start from scratch basically last night. And I'm hoping that I did this part correctly enough, because I was working on it until 10 o'clock this morning. Then I was back at it again about 2:30. All through the night I was working on it, and there might be some misspellings in here or something like that, and I just hope I have it put together good enough.
No, fair enough. Disclaimers aside, we appreciate you've worked till all hours, and race car driver excuses aside, let's get on with it. But yeah, fair enough.
We all know bollocks has 2 L's, Brian, don't worry.
Yeah. Okay.
Can you guys hear me now?
We hear you, Arwin.
Yeah,
yeah, because I had a little comment on the previous train of thought.
Go ahead.
I think I lost it.
Okay, do you want to grab a pen or something? Save it to the end. We'll crack on with the last section of the presentation, then we'll come back to you, Arwin.
Okay. Okay, this is good because a lot of people don't realize this. Most people refer to GPS as the global positioning system, whereas in fact calling it the ground positioning system would be more correct. But even more correct still would be to call it the geodetic positioning system, as all the map information used by GPS comes from geodetic and planar surveying originally. All GPS does is triangulate your position within a grouping of data known as the GIS, or Geographical Information System, which has this map data inside of it. Right, this is how it works. So they already have the map data, they already have the data there. All the original map data comes from, and all the surveying, all comes from surveying. And now all the surveyors get, all the geodetic surveyors get all their information from GPS. And I know this for a fact, as I know someone who is a geodetic surveyor, and one of the first things he told me was that years ago they used to have to do all this triangulation and everything else, and now they just get all the information directly from GPS. What he thought was just satellites in the sky. I didn't argue with him. I didn't go into that with him. I just was happy that he was willing to tell me that and tell me a few things about it, you know. So, but this is how it works. Okay, GPS is not a two-way system, right? It's not a two-way system, right? You do not interact with the source of GPS. You only receive from it. So unless you own a GPS receiver or something with a GPS receiver installed in it, all your GPS is provided to you via your phone's network provider. This here is a photograph of a tower that is a GPS assist tower. This is what they call these, GPS assist tower. So this helps basically, let's say things like phones and that don't have the receiver, the GPS receiver. And people think they have GPS receivers in their phones. As far as I know, most phones don't have GPS receivers in them, and computers and that, they don't have them, or iPads and that. And this, supposedly, towers like this take the data supposedly from supposed satellites and then send the data to your network provider, and then there's a whole rigmarole, which I'll go into in a minute. The GPS does what is known as trilateration to find your location and direct you to another location. This is just this is from surveying, trilateration from surveying. A method of determining the relative positions of three or more points by treating these points as vertices of a triangle or triangles, of which the angles and sides can be measured. Right now, basically, GPS use the same thing, right? Well, this is what they do. GPS uses high frequency radio waves and times the receiving of these microwaves to locate you. So I just want to point out the XY here. Okay, so they're always using Cartesian coordinate systems. This is you in the center, and these three are the three signals. You're the receiver here, and the time it takes for the signals to get to you, right, determines where you are. That's basically how trilateration. Now, trilateration would often have more than three, they'd have 4 and 5 maybe, but they often would have 4, maybe more. But three normally 4 and more to find a position where you are. So if you have a GPS receiver here, these three, right, signals, wherever they want to claim they're coming from, right, the timing that each one of these takes to get to you will determine your position. Okay, that's the starting of determining your position. Okay, right, this shows the same thing again. This is a GPS receiver phone in the diagram, and the timing of these signals to it, right, determines, right, where the person with the phone or the receiver is. That's all it is. It's just the timing of radio waves. That's all it is. If your phone is turned off, they can still triangulate you, right, with basic radio, right, with cell towers, right? They can do exactly the same thing with cell towers that they're doing with supposed satellites. And this is when you have GPS tracking. Let's say a truck or car has a receiver in it, and they take in the data, right? Sorry, the signal is sent to them, to these receivers, and it's received. It's not sent back, it's received by the receivers. And then this information, right, of where these receivers are, is once it's their once they use trilateration, is then sent to the cellular network, and then it goes from there to servers, to the internet, and then to your phone or device. So you're getting a tracking because of signals, radio waves, just microwaves that are being sent to receivers in a truck or wherever. So if you bought something off of eBay or something and you're tracking it, that's and it's en route, that's how it's been tracked, right? Or if you own a vehicle or a fleet of vehicles or something, you're tracking it, that's how it's been tracked. Now, all it is microwaves, right, hitting the receiver from different angles, from different places, different locations, right? They claim it to be satellites in space, as we all know, right? But we know that can't be. So wherever these signals are coming from doesn't matter. What matters is how it's working, right? And they have all the data of the maps. All the map data is already there. This is all part of what's known as a GIS, a geographic information system. All that data is there, and they know exactly where you are from them using trilateration at any point of where you are, because they can find you easy with just microwave signals. They can find you once you have a receiver. It's very, very easy. Okay, same thing here, right? These are all things that they are receiving. All these, the drone, the suitcase, the hikers, the dog, the motorbike, the car, the truck, these are all receiving this GPS. They're all receivers of these signals, right? And their data then is sent to a GSM network, and then through the internet to servers, and then to your phone and computer. Same thing again. That's all it is. Your receiver takes several microwave signals from several locations, and then this data concerning the amount of time the signals took to reach the receiver is calculated by the length of time each individual signal takes to reach the receiver. And from this data, your position is determined. That's how they do it, right? They just determine your position, but just by microwaves. That's all it is. They can make it sound fancy, but that's all it is. Microwave signals. That's all it is. Here, with airplanes, so I'm about to say something.
No, but I'll just add in, as you perceived an interruption that didn't come, that's a light, just for anybody who wasn't aware what microwave is.
Yes, that's right. Light. That's a fact.
Yeah, I was going to do the same thing earlier on with, is that photons? But what I wanted to say, Brian, before you do go on, that's brilliant, mate. You've really clarified, not triangulation for me, because triangulation has always been a great flat earth proof, but the technical data there and how they're doing it and boosting it and working it. I mean, it's always been obvious because, you know, I'm always accessible to the sky, yet my phone does seem to lose signal sometimes. So, and with the 5G, you know, that's coming up. So, yeah, cheers, mate. That was a good explanation and justification of how they actually get triangulations. It's not satellites, we all know.
Well, this thing about how they're measuring the speed, they talk about how they're measuring the signals because they know basically the speed of light kind of thing. But that is nonsense, because I won't do it here now, but I can debunk the speed of light. I know where the assumption of it started. It's so easy to debunk. Whereas their claim is that it's coming from space, right? Nobody can prove that it's coming from space. Right? Obviously, we can debunk space, but the point I'm making is they're just microwaves, and that's all they are. Just microwave that could be coming from anywhere. There's microwave transmission, and all microwave transmission works in a direct line of sight. Okay, so they're getting it from. We're getting microwave transmission from somewhere, supposedly. Maybe it's not. We're only told this. I don't know for definite it's microwave. It's just what we're told.
But microwaves are like light, but at a higher frequency, or like they reach further, you know? So they're still subjected to this. Sorry about my voice, by the way. Yeah, the trolls in chat are gonna have a field day. But yeah, it's basically like Nathan said, it's like light. It just travels like light does in a straight line. It doesn't go around some kind of R-based curvature. It doesn't go around a curve. It moves in a straight line like light, and it reaches further than light because of the frequency issue, but it's still subjected to the same principles as light.
Right on.
Yep.
Right, there's only about 10% left of the presentation. Do you want to carry on?
Yeah. Okay. Yeah. Okay. Aircraft receive. They have GPS receivers. They receive. Signals, and then they send the information they get to other aircraft and to ground control. Right. So it comes back to it's undetermined where these signals are coming from. Yeah, it comes back to that again, right? Because it's right. This is called NavSop, right? This is a military thing, supposedly, where they just use. They don't rely on GPS. They just use any signal from anywhere, right, to triangulate where their position. So they don't need this supposed GPS. They just use any signal, whether it be from anything at all. Every type of signal that they can pick up, they'll use to triangulate their position. Right? Because they don't want to be relying on GPS, because GPS can be blocked by, let's just say, another military can block the GPS in an area for one military, for an opposing military or whatever. So they just use any signal anywhere to triangulate themselves.
Well upset, Brian. Right. Cool. I understand that. That's plausible, unprovable. Who are the people that can use NavSop? Are they these same folks that we wouldn't be able to demonstrate to us for national security reasons and other associated bullshit, or is this a system that's available publicly?
Yeah, but that's the thing about it. You see, like they are claiming this, whether like this is kind of a higher level military, so the ordinary people wouldn't get to find out whether it's true or untrue. But
that's my point, Brian. What I'm meaning is,
yeah,
is this something that's available and out there, this NavSop patching, or is it something that's presupposed that in times of crisis the military can patch into it? And we think they're patching into, luckily that flyby jets just use my Wi-Fi router, as that diagram says, to GPS itself. Or is it an excuse for other technology they've got? What do you get me? This seems.
I honestly can't. I honestly don't know.
No, it just seems a bit fantasy in terms of excuses for why military stuff can do stuff that we can't.
Yeah, it's like they're not really what's really going on.
Well, like the old Malaysia flight, like they can track a military plane over the Pacific, but not a commercial jetliner. That's
easy now.
Sorry.
Right, let's move on.
I'm done.
Yeah. My only reason for putting this in here was because a claim was put out there, and I got this off a website that was talking about this. I think it was a military website. So it's just a claim is out there. So there's a claim that GPS is not even needed to find out where you are. So, but we'll move on. Right. You can also find out where you are with TV-based AM/FM. Right. TV signals can also be used to triangulate a person's position using AM/FM radio signals. Right, you can still be found with TV radio signals. The exact same way, they're just timing the signal. That's all they're doing. They're timing the signal. From let's say there's 3 signals hitting your receiver, and whichever one is furthest, they just time it like, okay, this is furthest because it took longest to get there, so we know this, we know that. And that's basically it. So, and we move on, right? The LORAN system. Okay, LORAN and DECA systems also use radio signals to locate something's position by using intersecting hyperbolic radio signals. So that's just a kind of a rough a rough diagram there. LORAN-C is a hyperbolic navigation system, operates by measuring time distance of arrival of signals from a pair of synchronized transmitters. By using 2 pairs of transmitters, a fix can be obtained. So it's all just back to the every bit of GPS, right? All their maps and everything, right, that they have as far as maps and all the rest of it, all that data comes from surveying, right? And all they have is that, and they add in, right? They have that, and they add in the timing of radio waves or radio signals, and they just find someone's location with those two things.
Isn't Loran? I know we keep throwing the ballers back to their 2017, 2016 arguments, but I remember Loran being one of the great flat Earth proofs back in the day, that the distance that Loran used radio waves to do demonstrated that it was only feasible on a flat Earth. It wasn't doable on a ball. Why they moved to GPS? Yeah,
there was Loran can, and Loran, they're bringing back Loran. Believe it or not, they actually proposed it in 2017. They're actually bringing back Loran, and it's actually still used by the US Coast Guard on that. And it has a 500 to 700 nautical mile distance. The DECA system is supposed to be better for mariners, but it has a 400 nautical mile distance. It doesn't have the same distance as the Loran, but it's supposed to be more accurate. Okay, but the Loran system has 500 to 700 nautical miles of a distance, daytime distance.
But that's not Duran. Duran.
That's Duran Duran. Oh,
it's not Duran Duran.
Hey, Kiwi.
Hello, Kiwi.
Hello. First.
Right, you're not first. Right, Brian, let's plow on.
Okay, Nathan. Okay. So all of these systems, whether it be GPS, NavSop, cell tower, TV signal, Loran or DECA, all just find the location of something or person using radio signals of different types and the length of time the signals take to reach the receiver. So they all work the same way. All locations are determined using radio signal timing. That's all it is, every single one of them. Right? Some of them are just more fancy than others. That's all it is. So this all brings us back to this. Okay. Now this is the part I want to, we're getting back to it. I'll make this a bit bigger if you can't see it correctly. Can you see it correctly on screen?
Perfect. It's perfect. Scaled nicely.
Okay. This here is supposed to be right. This is they're saying point on the Earth's surface right here, right, and this is making the tangent the zenith from above that becomes a tangent to the center of a supposed sphere, right? This is what it is. But what they're not telling you is earlier on I said that they're using this Earth-centered, Earth-fixed coordinate system is what all satellites used. So basically, a satellite is supposed to get your position right on the globe, right, and then it makes a zenith, right, it makes a zenith, basically, once they have your position, there's a zenith comes from the sky, and it makes a tangent to the center of a sphere, okay? Right. The red line shows what would be a zenith angle, right? Now we're back to this, right? So your position has been found by GPS here, right? This is you, let's say the H, the purple line, and this is your zenith here that goes into the center of a supposed sphere, right? This is you on the tangent plane, right? So they find you within the data, right, with trilateration of radio signals, microwave signals, and then they make this zenith, okay, that goes into the center of a supposed sphere, right? And then we're back to this, right? Now, I just want to go, right, read this down here first. The ECEF coordinate system above assumes a globe, and all zenith angles are pre-assumed to meet the center of a globe Earth with a radius of 3,959 miles.
Bullshit. Bullshit.
And we know about the radius value, question mark. It doesn't have
guys, this is the conclusion. Just let him make the conclusion. Save the jokes till after. Thank you.
Okay.
Sorry, guys. Sorry, Brian.
You're welcome. Sorry. I'm a worm.
And the next step, right, is this, right, as we saw earlier. So once they have established this much, right, with this as a zenith going to the center of a supposed sphere, right, the next step is, right, on the tangent plane, which is the flat area here, to make, right, basically one big massive load of Cartesian coordinate systems, or one big Cartesian coordinate system, Okay, the Z here, or zenith, is the perpendicular to your tangent plane. Using the ECEF coordinate system allows them to still use Cartesian coordinates while pre-assuming a globe. And when asked for information on this, they will give you zenith angle information, which, because of all zenith angles are already meeting at the center of a pre-assumed globe, won't be perpendicular to each other. So this is my point. If you, let's say we're here, this is like where Ireland and Britain is, right? And we come over here to, right, the US, let's say down here to where QE is, and you take a zenith, let's say QE's zenith and Adam's zenith, right? They're going to meet, right, here, both of them are going to meet in the center of a pre-assumed sphere, right? So when they get the data from when they get the GPS data, right, which will all be in Cartesian coordinate systems, right, when they get the zenith, or where this supposedly was, it's all calculated back into a globe. So then when you ask what is your proof of a globe, they'll give you two diverging zenith angles. They won't be parallel because they're on a globe, because they already pre-assumed them to be on the globe. So when you ask somebody like, let's say Jesse Kozlowski on the globe side, he could very well, or another geodetic surveyor, give you, right, diverging zenith angles, because they're all using the ECEF, Earth-centered, Earth-fixed version of Cartesian coordinate systems, which puts everything into a flat plane, but it gives diverging zenith angles. Do you understand what I mean? Because if I'm over here, if QE over here has a zenith angle in here,
sure. Rather than you just repeating yourself, I'll just summarise it in a slightly different verbiage. So for my audience, where I draw a line here, this is what BevTri thinking covers. So if you imagine this to be a disco ball with lots of tangent planes all together, when you did some surveying on this particular section, you're never going to have the next section along, which has a completely different zenith, according to their presupposition, giving you an angle along this line. Everything from this point to the next will still be flat. However, their assumption would give you diverging zeniths. And based on the Cartesian coordinate system that they're using, everybody needs and does have, within their own tangent plane, a single zenith. So therefore, you're not going to get this line joining up with another one and an angle and loads of stuff that's not, perpendicular to each other. You need perpendicular in Cartesian coordinates, and all they do is give it you in a fixed area called your tangent plane. And Brian's point, to summarise, is that if you're over here in the States, you've got a completely different zenith, and they need to be parallel, not converging at a point in the centre based on their presupposition.
So what you're saying is that the Cartesian coordinate system must be based on a flat Earth.
Correct.
Is that what you're trying to say to me?
Yeah, all Cartesian coordinate systems are based on flat Earth. But this one, the Earth-centered, Earth-fixed, the Earth-centered, Earth-fixed coordinate system, which is the ECEF, is a Cartesian coordinate system. But before they do the Cartesian coordinate system, which is here, which is XYZ here, they first pre-assume that the zenith is going to the center of the globe. So then when they get two zenith angles from two different locations, they always have diverging angles. So then, yeah, it's a globe. Of course, it's a globe if you're going to send your zenith into the center of a pre-assumed sphere.
Right, but it would necessitate it would necessitate each tangent plane meeting up like a disco ball.
Yes.
I think it's a bit worse than that, isn't it? I think what Brian did early in the presentation was demonstrate these XY coordinates. And what the ballers want you to do is set up that little square, that little plane, as if that's the reality you can measure. So they set it up like that for you for ease of understandability. But the reality is that there's only the point where that zenith it meets, that plumb line that you drop. That's the only point in that whole even grid that actually has those coordinates, that match. There's not, you move 1 millimeter to the left or right, north or south, whatever, and your coordinates change and your angle, more importantly, changes.
Yeah,
So-
or to point out the flaw, if you will. If, again, for the audience's benefit, if I start on the very edge of the tangent plane, this tangent plane in their coordinate system has up, and I'll just draw it for the audience, running parallel to the original center point zenith. So this line has still got up running parallel. The whole plane has. Any edge will have up parallel. Now the fact that in that tangent plane, it has to be, because it's utilizing Cartesian coordinates, their globe map has that tangent plane, the very edge of it, with a completely different up pointing out here, but on the plane that they're actually going to utilize, this square, up will be running parallel, but it won't be in terms of their model. So it's a very obvious squaring of the circle.
Even in the square they draw, up is not up at the perimeter of the square. Does that make sense?
Yeah, I'm saying that you've got...
Up is only up at the center of that square. Anywhere else on that square, 1 millimeter away from up, it's no longer up.
In reality, if it was a sphere, but on their plane that they actually utilize, the edges for that particular tangent plane are all running parallel to the zenith they drew from the center point.
Yeah, Adam, this square here is treated as totally flat. So you can have a zenith anywhere here, and it'll be exactly parallel to the zenith in the center.
So that then is turning that into a
flat plane. It's turning it into a flat plane. In other words, Adam, if you drop a plumb line from the center, it drops down. Now, if you drop a plumb line from this very edge, and all your assumptions in place that you're assuming a ball, you're still going to drop a plumb line and it go down, and it will absolutely be parallel with the zenith that you assumed with the presupposed tangent going to the middle. Radius value to the middle.
Yeah.
So you're still going to have a plumb line run parallel, and that's how it works in reality. The edge of this tangent plane that they draw will have a plumb line run parallel to the center point, because we are on a flat plane.
Yeah, so, but the point being, if you were to draw another parallel line equal to your zenith line on anywhere on the perimeter, if it was parallel to the zenith line, it would not meet the center of the ball.
Correct.
Yes.
Correct. But because that doesn't happen, in other words, you don't move an inch to the right and have your zenith change because you've moved an inch around a ball, you have to project out a flat plane to work on and assume that even at this edge, because that's what you have in reality, a plumb line will match somewhere else on the flat square that they've drawn. Because it does, and that's only because we do live on a flat plane.
Yeah, exactly. That's exactly it.
The pretense there is then that the ball Earth is no longer a ball Earth. It's made up of multitude of Bolivian salt flats. It's a multi-sided polygon
disco ball, exactly. Mirror ball.
Yeah, mirror ball is a great example.
But we'd need to see some edges to those mirror balls. But that's just their squaring of the circle, getting around the fact that plumb lines do run parallel. Cartesian coordinate systems rule for a reason, so they have to utilize them within the parameters that you have plumb lines that run parallel. Now, their presupposition that they started with doesn't have them running parallel, which means that's just the flaw in this system. They have to square the circle. We are on a flat plane.
Yeah, exactly.
That was a good line you had, Brian, in that quote earlier that said it all. For them to do it accurately, they have to measure it as if it's on a flat plane. So they have to deal with reality to do anything accurately, and then convert it back to a ball. But if they tried to measure it as if they were on a ball, it doesn't work. Which is why they have to set up that grid you demonstrate there, because that's what the surveyors work with, a flat reality.
Yeah, they have to pre-assume that all the zenith are going to the center of a sphere. They have to, otherwise there is no sphere.
Okay,
where's that center? Excuse me. Where's that center of the sphere again?
Well, it's not really around anymore.
That's what I'm saying. The entire base is going from the center of a sphere with a certain what?
I know.
Radius?
We're getting to it. Don't worry. I didn't.
Okay, we're getting there. Sorry about that.
We're getting to it. Don't worry about that. We didn't
Okay.
forget about that.
Right. Did you want to move on? Because there's still a bit more.
Yeah, there is. Yeah. Okay. Yeah. Okay. And I think I read this out, right? And the next step with this, I read this out. Yes, I read that out. So the next part. Okay, I came back to this again, right? Just to show again, right? Because it was important. GPS data correction using encoders and inertial navigation system. Okay, the local geodetic frame or tangent plane frame is the northeast down or northeast up rectangular coordinate system we often consider in our everyday life. So they're telling you there that they're using, once again, they're telling you in this this part here that they're using rectangular coordinate systems, which is all rectangular coordinate systems are Cartesian coordinate systems. So they're basically telling you, yeah, we're making all this flat, but the zenith is going to be to the center. That's what they're going to, the center of a pre-assumption. Okay, it is determined by making a fictional tangent plane at the origin, right? Just like presenting the globe as a map. The x-axis points north, the y-axis points east, the z-axis points towards the interior of the Earth, normal to the reference ellipsoid. Right, that's what they're basically saying. They're following the ellipsoid radius at that point. Okay. Right, Cartesian. This is from. I actually got this from the Irish Geodetic. I can't remember the name now, but it's like an official website or whatever. This is Cartesian reference system. It is important to realize that the center of a Cartesian reference system for an adopted ellipsoid may not be the true or adopted center of mass of the Earth. The latter is often used for global reference systems, as used by the Global Positioning System (GPS). Furthermore, the direction of the z-axis may differ. Right, that's important. The direction of the z-axis may differ. Yes, because it will differ. Right, if you're using it on a flat plane or using it on a globe. Right, this has led to one of the major requirements of Geodesy and surveying today. Which is how to relate global to local referencing systems so that positions in one may be expressed in terms of the other and vice versa. This issue is not dealt with here except to state that it is necessary to move from the ellipsoidal system to the local Cartesian reference system before applying some translations in X, Y, and Z, and possibly scale change and rotations around these axes as well to move from the local system to global. Now, this part here is important. The Cartesian reference system is particularly useful as calculations are simpler to perform, no knowledge of spherical geometry being required. However, the relationship between positions on the Earth's surface are difficult to visualize in this system. And this is particularly important with navigation. For instance, the concept of height is also unclear. Right? Cartesian coordinates are simpler to use because they show reality. Z-axis may differ, ? Yes, when one is referencing the sky and one is referencing the center of a pre-assumed globe, the z-axis will definitely differ then. Right? Of course they will. If you have your z-axis is going to be parallel on a plane, but if you're referencing just the sky, it's going to be parallel. But if you're going along with a pre-assumed model of a globe, right, then and everything meeting at the center, it's going to be different. Okay. Now, this is the same as I showed you earlier, but is a better version of that diagram, but clearer. Right? The source is GPS for land surveyors. Okay, so this is showing exactly what they're using. This is what they're using. This GPS uses this coordinate system, right, which ends up being like the tangent plane, like a whole area of the Earth will be seen as Cartesian coordinate systems, and it'll be surveyed like that, right? But GPS is always using Cartesian coordinate systems, but they're always pre-assuming the zenith into the center of the supposed sphere. Okay, this part here is not important. I'll read out this part though. This part here. A spatial, so some geodetic coordinate systems, three-dimensional 3D Cartesian coordinates. A spatial Cartesian system with three axes lends itself to describing the terrestrial positions derived from space-based geodesy. Using three rectangular coordinates instead of two, one can unambiguously define any position on the Earth, or above it for that matter. The three-dimensional Cartesian coordinates x, y, z derived from this system are known as Earth-centered, Earth-fixed coordinates. It is a right-handed orthogonal system that rotates with and is attached to the Earth, which is why it is called Earth-fixed. A three-dimensional Cartesian coordinate system is right-handed and handed if it can be described by the following model. The extended forefinger. This is just telling you about that part is not important. Just telling you about how they use a right hand to show that's only for the positive of Cartesian coordinate systems. According to the diagram above, the zenith can be at any angle. Yeah, this is the point I'm making here. Zenith can be at any angle. Like to us, zenith is up in the sky, but zenith, according to these people, is from anywhere. Your zenith at any angle. So zenith is supposed to be 90 degrees, but according to this belief here, it can be coming in at any angle.
Oh, that smells like ball of bullshit subterfuge. That it can only be any angle if you're describing it from the observer's point of somebody else. So zenith is only ever going to be up to you. For it to be something else, for you to pretend on it, you've got to go to somebody else, pretend you're on a ball, yeah, calculate the distance between the two of you, calculate the angle it generates, and then make a mathematical statement that person's zenith over there is by this many degrees different to my zenith.
Yes, exactly. That's exactly what it is. Yeah,
shit houses, aren't they?
Yeah,
is the honest way of describing that. It's dishonest and deceptive in what they're implying.
Okay.
I think a lot of these people though they just don't know any different. That's it. They don't know any different.
You're nearly at the end of the presentation now, so we'll discuss it earlier and hopefully bring in some of the public opinion as well. So do you want to plough on? We'll get to the end and then hopefully we'll open up the discussion a bit.
Okay. I'll read out this part here. Looking straight up can be at any angle. I'll put a few question marks behind that. It is important to note that the GPS control segment generates the position and velocity of the satellites themselves in ECEF coordinates. It follows that most modern GPS software provides the GPS positions in ECEF as well. Further, the ends of baselines determined by GPS observation are typically given in ECEF coordinates, so that the vectors themselves become the difference between those X, Y, and Z coordinates. The display of these differences as dx, dy, and dz is a usual product of these post-process calculations. Like basically what they're telling you there, that they're telling you that like they can basically take what they've. I'll read it here, what I'm writing about it, rather than trying to speak about it. This basically says that once they have gotten all the information from GPS, which will be in flat out X, Y, Z Cartesian coordinates, they then can proceed to stretch and warp it into any other differing system. All of the information comes out as a GIS, Geographical Information System picture below. This is what you see as GPS map data on your device. This is just an amalgamation of geodetic surveying Cartesian coordinates map data and then planar surveying map data as you zoom into a particular location. Your location is found through radio signal trilateration, and then you will be guided to your chosen destination, which is also found by radio signal trilateration. And this happens through the use of software maps that have all come from surveying and cartography before any software GPS system. Okay, this is a GIS here, right? It's just a collection of data. That's what you end up with on your phone, right, from GPS, right? It's just a collection of data. So you have street data, building data, vegetation data, and integrated data. And you always end up with this flat plane on your phone showing you, and it doesn't put you wrong. There might be road work somewhere or something like that, but other than that, it doesn't put you wrong. Everything is as it shows, on your phone, the flat map on your phone. This is GIS, or Geographic Information System. Okay. I'm not going to read out all of this, but just this line here. Distortions can be computed and then either eliminated or reduced to negligible levels. What they're talking about there is the distortions between what they believe and the reality. So they're going to have everything in Cartesian coordinate systems, and then they're going to have to try and change that to the reality they want, which is a sphere. So that's why obviously they have the ECEF where where the zenith goes into the center, but of the supposed sphere. But that's what they're talking about. They're distortions. There shouldn't be distortions, except for they have to make distortions. They have no choice. Okay, there are tools to transform the data so that they are all in the same coordinate system. With these tools and the proper knowledge, the geomaticist is free to mix and match data with an understanding of the compromises and trade-offs inherent in each decision made along the way. There are tools to transform the data so they are all in the same coordinate system. Yes, these tools are known as the XYZ Cartesian coordinates. And by using these particular tools, one can change the results to suit any chosen model. XYZ is the flat benchmark for all models. So everything you're getting is in flatter coordinate, is in Cartesian coordinate systems. It's all surveyed in Cartesian coordinate systems, and GPS use Cartesian coordinate systems all the time, right? And then they change it to whatever they want. So it's like having a flat, or like having a blank canvas. That's what it gives them, a blank canvas, to do whatever they want with after that. Okay, the need for flatness. These parts you're going to enjoy. I have to read them out. It's going to be a little bit of reading. Only just two or three paragraphs. Cartographic products are flat, whether they are paper maps or images or on a computer monitor. Maps are flat for many reasons, some rooted in convenience and others stemming from psychology. Humans tend to think of distances as being straight line distances. We are comfortable with the idea of a horizontal distance and a vertical distance. And we know that they are measured with, say, a measuring tape pulled taut in a straight line. We tend to think of our environment as being flat, and we are very comfortable with, and in fact, we prefer depictions of space that conform to that perception. The convenience of a flat model of space is clear. Globes don't fit in a glove box of a car, and they would have to be very big to show important details. Sorry? You say something, Nathan?
No.
There's a bit of feedback, sorry. The convenience of a flat model of space is clear. Globes don't fit in the glove box of a car, and they would have to be very big to show important details of small regions. We usually want to determine distances by laying a ruler on the map and multiplying the measured distance by a constant map scale factor. In fact, for distances measured with a ruler on a map to be valid in all circumstances requires that the Earth actually be flat. Okay, for them to actually do any real measurements, they have to treat it as flat.
That one's worth rereading. Just read that once more.
In fact, for distances measured with a ruler on a map to be valid in all circumstances requires that the Earth actually be flat. So it requires it for it to be correct. Now, the round realities, regardless of our perceptions.
Hold up, because that's immense. How do you define those measurements? Do you know what I mean? And confirm them, and that in fact, for distances measured with a ruler on a map, I mean, I want to subjugate a little bit to say, well, yeah, that could mean the map's corrupted, but
no, it does mean the map. Hold on, that was implied. That does mean the map's corrupted. The maps that are being utilised, this is doublespeak for saying they don't work, and for them to work, well, it would have to actually be flat, and we're not flat, we're a sphere, that's why they don't work. Not because the maps are corrupted in any way. That's the doublespeak magic trick.
Thank you for saving me there, Nathan. I knew something was wrong, and I couldn't get do you know what I mean? That's, yeah.
Well, sorry, Nate. Sorry, Adam, I thought you were finished.
No, I am. I was thanking Nathan for saving my arse there.
They're always telling us for our whole lives that maps are wrong, right? Even though flat maps are wrong, even though we use them all the time to find out where we want to go, right? All the time, we always use flat maps, whether they be paper or digital. We're told they're wrong. They're not. We're told they are not reality. Reality is actually a big globe. This is what we're told. And that flat maps have to be distorted to fit around the globe, right? No, it's the other way around. It's the other way around. It's the globe is wrong. There's nothing wrong with flat maps. The globe is wrong. There's nothing wrong with flat.
Right, and what maps do we have? Do we have flat maps? Well, no. Yeah. We have globe projections.
Yeah.
But they're only wrong when they're on a flat map because Earth's not flat, is what that statement's saying.
Well, this is what you're dealing with.
Yeah.
Is that not double speak? Because that would then, if you
know the context for what's being read,
to say that flat maps would be a representation of the Earth.
we don't have accurate maps. That's the fact of the matter.
I'm happy with that.
Yeah, but they're blaming it on the fact that if for them to be accurate, they're saying, well, the maps, we'd have to actually be on a flat plane. So it's a very complex little trick designed for the surveyors specifically. So obviously the context isn't for us to take it out of context and say, well, there you go, they're proving the Earth's flat with this statement. No, what they're saying is all of the maps are distorted and wrong, but they're not phrasing it such. They're saying the only way they could be right would be if it was actually flat. So it's a kind of reverse programming for the person reading the manual. So the person who reads that goes, well, yeah, I understand that. Obviously, we've got to project them for convenience onto flat pieces of paper, but they're never going to be quite right because obviously Earth's a sphere. That's the cognition you're left with after reading that statement.
Yeah, the maps aren't right because it's a sphere.
Yeah, that's the cognition you're left with. Now, of course, that's total bollocks. That's where you're going, hang on a second, this doesn't add up. Well, yeah, but we're not given any flat maps to say, well, look, this one's perfect. And when anybody tries to present a straw man argument of here's what you call a flat map, no, it isn't. So when the azimuthal equidistant projection from the centre was North Pole centric, rather, was presented earlier, that's a globe projection. It's not a flat Earth map.
Yeah.
Exactly.
Anyway, Brian, do you want to carry on?
Okay, yeah, I'll read on the next part. Round realities. This is actually in some ways better. Regardless of our perception, the Earth is round. Perhaps the most apparent contradiction of the flat Earth hypotheses comes from watching ships as they approach land. If the Earth were flat, then ships would suddenly pop into view and be visible from their waterline to the top of their masts all at once. This does not happen. The top of the mast come into view first, with the hulls appearing last. Sailors describe ships as being hull down if their masts are visible, but the hull is below the horizon. Of course, images of the Earth seen from space are pretty compelling too. Now, I looked into this hull down thing.
Hold on. Have you changed documents? What's going on? Why have we suddenly got a fundamentalist religious zealot argument? I thought this was a geodetic surveyor's document. What's going on?
This is.
Hold on. Someone's chuckling. What's going on? I'm a bit confused. I took my eye off the screen for a minute. Did you change the document?
No, that's the same exact one.
What's going on? What's going on?
There's evidence, mate.
Oh, wait a second. They went back to 2015 and then pulled their little child wreck argument in as a preface to the next paragraph.
Hold on. This paper isn't a debate paper. This is
am I
losing
not
the plot?
Poisoning the well paragraph prior to the underlined one?
What This is why we're all hoodwinked by people like geodetic surveyors, because when they're trained and when they get their documentation, this is what's in there. My God, yeah, why not sprinkle it with a little bit of fundamentalist religious zealot globe programming?
Yeah, exactly. And they contradict themselves in the next paragraph. Will I read on?
Be my guest. I'll try and contain my exasperation.
Oh no, it's good if you don't. It's good if you don't.
Yeah. I mean, I was put down for interrupting. I'm sorry. I should have been running the show.
Come on, hey Westlife, get on with Zebediah the Surveyor, chapter 13, verse 4.
Okay. Right. For the purposes of making maps, can't we just pretend that the Earth is flat? Could we, for example, just treat latitude and longitude coordinates, which are angles, as if they were Cartesian coordinates, which are linear distances? Question mark. For that to work, geographic coordinates would need to have the same properties as Cartesian coordinates, but they do not. For example, every point in a plane has a unique pair of Cartesian coordinates, x, y. But what are the coordinates of the North Pole? Its latitude is 90 degrees, but what is its longitude, right? Now, this is what I wrote about it. But what about the North? But what about the North Pole? What about it? For that to work, geographic coordinates, latitude and longitude, would need to have the same properties as Cartesian coordinates, but they do not. This man has fooled himself by proclaiming that flat can't work because it's a globe, in his own words. But what are the coordinates of the North Pole? What about it? Like, he came up with a reason, right, to make it all go away. That's in his own head. That's what it seems like to me. Came up with a reason here to make it go away.
So a bit of fundy zealot programming, and then the author spilling out as a projection in the text. My God, this is really eye-opening.
Yeah, this is horrendous. Anything else to say about that part before I go on?
Anybody?
Nathan's aghastness was sufficient.
Okay. Moving on then. Okay. Step 6, finality of the presentation. The Jesse Kozłowski audio clip section. I sent that to you earlier, Nathan. It's in your Skype.
Yeah.
Yeah, I'll leave you play it.
Oh, do you just want me to play it now?
Yeah, I'll leave you play it now. Yeah, this is that point. Because I didn't know if it would come through on my end.
I've got 3.
I sent you. I sent. There was the first one, and I sent you another one, which was a cleaned up version. It's called Jesse.
Jesse AIF.
Yeah.
So here's the thing I wanted to explain. GPS operates in a 3D Cartesian coordinate system. It is not latitude and longitude. That latitude and longitude comes from a conversion from that box style system. That's the native coordinates coming out of a GPS system.
That's it.
Perfect.
Just thought so no one could argue that is from the horse's mouth, from Jesse Kozłowski himself. Okay. In this audio clip, Jesse Kozłowski is referencing the ECEF Cartesian coordinate system, which, as we covered earlier, pre-assumes a globe by bringing your zenith angle through an imagined sphere to its center some 3,959 miles deep. But this allowing the usage of XYZ flatter Cartesian coordinates for surveying purposes, as flat is much easier to work with, as it's the actual reality we all experience. But when he's speaking about GPS, he's also speaking about this zenith to the center of a supposed sphere. So he's not saying, or he's not thinking, that this whole square here is all going to be based on flat, right? And that's what GPS is going to be working with. But GPS is also going to be pre-assuming this tangent to the center of a sphere, and how GPS over here will be pre-assuming a different angle to the center of a sphere. So the reason I'm saying that is that if you listen on to what he says after that, he starts trying to back up the globe, but it all comes from this pre-assumption. They start out with this pre-assumption, and then they start surveying when they make a tangent plane. That's when they start actually surveying. They don't survey any of this stuff. None of this is surveyed. This is just pre-assumed before surveying. Then they start surveying on this tangent plane, where it all becomes Cartesian coordinate systems. In response to the ECEF version of Cartesian coordinate systems, I present this, right? In response to this nonsense up here, right, about this tangent from the zenith to the center of a sphere with a radius of 3,959 miles, I present this. And I present this. And I present this.
Hold on, just for anybody who's listening audio only, just tell them what you're presenting.
Okay. I'm now presenting, right, what is the black swan photographs, okay, from Santa Barbara. Okay, this one here shows shows the curved tangent that is needed for globe geometry. Okay, and all about this here is all talking about how it all works, right, on the left. Then on the right, at an 8-foot elevation height, the globe Earth horizon should be less than 3.5 miles. Yet they have platform C at 6.8 miles away, and they have platform habitat with 10 miles away, with an horizon past both platforms. Okay, and there is a bigger version of that exact observation with the horizon past the 10.10 miles from an 8-foot observer height. Right, where the horizon should be no further than 3.46 miles.
That's copyrighted, by the way.
Just let me just summarize it. So if the Earth was a sphere with a radius of 59 miles, then every distance to horizon can be no more than 1.2 times the square root of the observer's height in feet. And what Brian's presenting is distance to horizon way in excess of this parameter laid down by a sphere Earth with a sphere Earth horizon, debunking the notion that we have the R value that they're using when they beg the question before they make any measurements. So he's debunking the R value with the black swan, which ultimately collapses all of geodetic surveying's presuppositions. Good job, kudos.
Yes, exactly. This is a 1 foot observation height here. And at 1 foot, the horizon on a globe with a radius of 3,959 miles will be no further away and cannot be no further away than 1.23 miles. Here, it is past 9.4 miles from a 1 foot observation height. So going on that, this has to be rubbish. That alone totally debunks this. It has to be
Precisely.
rubbish. So that destroys that. And for the very, very end, and for those who want to still assert that we are getting these GPS signals from space, solve for X. Condensed helium in a can. That's the end of the presentation. Thank you.
So how can you have gas pressure without the necessary antecedent of a container? So you'd need to prove space if you're going to prove that you've got satellites orbiting with the presupposition of an orbit also in place. Excellent presentation, Brian. Very good indeed. Thank you very much indeed. Bravo.
Thank everybody for getting involved in it.
Yeah, cheers, Brian. Great presentation. Great brand of helium gas, by the way.
So, panel, do you want to make some comments, jokes? Yeah, QE, do you want to go first because you were like precisely that summarizes it excellently?
Yeah, there's some major problems. This is too easy. WGS 84, the flattened ellipsoid, you're using for your GPS, people. Can somebody call NASA? They need to redact some of the images that they have. Okay, please. That's number one. Center of the sphere. Can you tell me where the center of the sphere is? How you came up with that? Ballers? I'd really like to know that. Has anyone been there? Or did you just calculate it? I bet you just calculated it from Booby Al-Baruni. I'll bet that's what you did. How do you, like I said, how do you even know where the center of the earth is? You just conjured it. And satellites, just because satellites work, right? This is the old 2014, 2015 trick. Just because something works doesn't ipso facto mean your fairy tale religion is the base of it, clown shows. Because you see, satellites in space, in Narnia, they can't exist there because it's a second law of thermodynamics violation. Did you guys forget about that? Second law of thermodynamics violation. And lastly, Jesse Kozlowski and your theodolite and all you numpty dipshit total station fruitcakes. I got 3 words for you. Angular size change. Thanks. Have a great day.
Got anything, Adam? Thanks for that, QE.
Thank you.
Well, firstly, Brian, wicked, mate. On some of the detail in there, I learned a good few chunks in there.
Thanks, Adam.
But fundamentally, for me, you outlined that it's a mirage. So look over here, right now. Look over there. Yeah, don't look at what this hand's doing. Do all this stuff, which amounts to naught. Then deal with reality. Yeah, and then backweight your numbers if you want to pretend it's on a ball. And I think you really did demonstrate that in numerous points, Brian, how the subterfuge is there, both in terms of the way they're saying surveyors are mugged off, or how ballers who think they're surveyors describe what surveyors are doing are mugged off, more importantly. I don't think surveyors are. Lucky enough to know, I've met one on my flat earth journeys, and he doesn't describe it in any way that the border surveyors, pretend surveyors do, and he's a real surveyor. So there's that, and I think I'd say fundamentally it showed to me that it's deception that they're dealing with here. I think you outlined that really well, and yeah, cheers, pal, for quite an informative bit. There's a good few bits that made us interrupt, which is always a good sign. You know what I mean, of a informative thing.
Arwin, have you got anything to add? Thank you, Adam.
Who's that man, Jay?
Arwin?
No, not really. I'm just resting in the background here.
Just having a rest. Okay. We do also have a peanut gallery, so we do have a Discord server with a few people in. So was there anybody in Discord that wanted to add anything before we round out?
Excellent.
Thanks, Steve.
No, I say I get in trouble. That's why I didn't want to talk. I said excellent.
Thanks, Steve.
Any more for any more? Any comments? Anybody at all?
What do you mean anymore for anymore? This was quite a long presentation. It took you geodetic surveyors and your GPS prognosticators. Where are you? Come on.
Anything
you
to
can come
add?
in here.
Dave?
I've got a quite technical question for Brian. If I was stood here, where I am, right, Westlife, in Nottingham, and I started to draw my geodesic map around me, and bearing in mind that wouldn't be a sphere, would it? Because if it was a sphere, this geoid, and wherever I was, it'd be the same. It wouldn't be a problem. And then you did the same, and we drew these maps on this year. Would they be the same? Would they be superimposable?
As in, would they, if we did it honestly, would they be both flat?
Well, remember where you are is the top of a geoid, a flattened ball. So if we move across the Irish Sea, a few hundred miles, and then we redefine the top of that flattened geoid, is it a definitive shape, or is it a way of perceiving something that you want to be flat, but you have to you want to be a ball that you have to try and make flat and convince yourself you're doing things? And that's what the geodesic survey to me is. It's the first step in the bullshittery of convincing people that what they see as flat is, this is why you don't see as flat. And the geodesic thing is quite fundamental in that it requires a realignment of the flattest part of their geoid to be wherever you start measuring from.
Exactly. Yeah. What would be the difference is, because of where I am and where you are, there would be different tangent planes. So they would have a different zenith angle in their belief. And that would be the only difference. Because my tangent plane and your tangent plane will be in two different locations. And because it's pre-assumed to be on a sphere, they're going to have two different, they're going to have diverging zenith angles. So, that's what they would do here and what they would do there or anywhere else will be the exact same thing. They're going to have to make it flat to survey it, because it is flat. They can't survey a curve they can't see. And they can't measure. They can't do anything about it.
You want to, anybody in Discord, if you want to pipe up, feel free. They're all open mics, so feel free to chime in if you want to.
Mr. Satellite, Mr. Vapor is not a gas. Professor Phil Belland, I see you out here in chat. I just pulled up the live stream. Mr. Satellite, do you want to come on in here and tell us your story?
Got Fundy Lamental. Did you want to add something? flashing, but we can't hear anything. Hello, Neil. Hello, Dave.
Hello, hello.
Hello, hello.
Oh my God, you got Sean the Crackhead Hawkins in here too. Vapor is not a gas.
If we're just going to assess the chat, I'll round out shortly. Last call.
No, I want them to come in here. I want Mr. Satellites, and vapor is not a gas. Is the stupidest thing I think I ever heard. Professor Phil Belland, Mr. Satellites, Mr. Water Satellite guy. I don't know. Professor Water. I don't know. To come on in here and give his take on this presentation. That's
Shouldn't
fair.
GPS and Professor Phil be in here?
Yes.
You would think so. Well, last call.
Should Professor Phil not be a big anti 5G exponent? Is it?
Don't start.
What's it out of business, does it though? Is that why they're investing all this money into ground-based communications?
Professor Phil Bell, what? You whistling past the graveyard, son. I destructed you with like 60 points. And you're just out here whistling past the graveyard. Come on in here. Water's warm.
One last late arrival, Enigma. Anything to add?
Yep, I just came in, so not really.
No, fair enough. I think that's going to be where we close out the show. So first and foremost, a massive, huge, enormous thank you to Brian for doing that presentation. It was absolutely superb. And of course, a massive thank you to all of you in the live audience for tuning in, hopefully smashing the super chat, liking, commenting, sharing, subscribing, and all that good stuff. Now, there might be a short after show to follow, so stay tuned if you're watching it on a premiering stream, as we'll chat a little bit after this live stream is over. There is a premiering stream running at the moment, so if you want to tune into that, I will spam the link in the live stream chat once the intro is over, so check it out again on the Nathan Oakley 1980 channel. Once again, a massive thank you to Brian's Logic for the presentation. I've been Nathan Oakley. Stay tuned if you're watching on a premiering stream, and I'll see you all in the next video.
Oh, what a day! What a lovely day!